Here we're going to do number 25. Number 25 is a one-star problem. It's giving us this little bit of a crazy situation here where we have a uniform beam and they give us the weight of the uniform beam, and it's holding up this crate, and they give us the weight of the crate as well, and it's being pushed up against the wall and it's in equilibrium, and they want us to find the magnitude of the tension in the wire that's connected to the wall and the magnitude of the horizontal and vertical components of the force that the wall exerts on the left end of the beam. So we are focusing in on the beam, so we want to include all the forces acting on the beam. So the first thing we do is we draw a free body diagram, or just a regular diagram with our forces acting on it. We have that weight of the box pushing down on the beam there. We have the tension acting at a 50-degree angle there. We have this force 1 that's going to push back on it. But we are also going to have to remember the weight. Remember, this thing has a weight. We have to start taking into account the weight of the actual object. And we have a second force pushing up on it. We have to have the second force. One, the problem told us there's a X and a Y component acting on the wall. But we have to also realize that if we had set our reference point at the beam, we need something there to cancel out some of the torque caused by the other forces. And we can actually solve this now. So like before, this is an equilibrium problem. So we know the net force in the X and the net force in the Y, and the net torque all have to equal 0. We have a lot of unknowns. We can start with our torque equation. We set up our reference point there. The reason we picked that reference point again is to eliminate the most number of unknown forces. So by putting the reference point there, we know the torque caused by F1 is 0 and the torque caused by F2 is 0. So the only object we don't have to into account is the tension. So we can actually solve for tension. Now, since the tension is acting at an angle, we got to be able to break it up into its kind of a X and Y components. And then to find the torque, we take the Y component and multiply times the X component of the displacement, and the X component of the force times the Y component of the displacement, and that'll give us the torque. It's the easier way than trying to figure out the whole angle, especially when something like this is kind of complicated. So we start with net torque is equal to 0. So we have 1,960 times L cosine theta. We use cosine theta to find the X components because 1,960 is only acting in the Y direction. Plus T sine of 50, which is the Y component, times the length in the X, plus T cosine of 50, which is the X component, times L sine of 30, which is the Y component of the length. Plus, we have to account this 1220 is caused by the gravity, and it's a uniform beam, so the gravity acts exactly in the middle of the beam, so it's halfway across the X direction. And then we have our equation there. We can clean up the equation because there's an L component for each part, so we divide everything by L, and we get kind of something nicer that we can fix up a bit. Now this looks much more complicated than it really is because we have to keep in mind that sine and cosine, since we know all the angles, we can plug into our calculator and get real numbers and kind of make it a little cleaner for us to figure out. So once we summarize everything, it just pretty much now T sine of 50 cosine 30 plus T cosine of 50 sine 30 equals to T times 0.98. 610 cosine 30 is 528.27, and 1,960 cosine 30 is 1,697.40. We can clean that up still a little bit more, and then we find out that the tension is 2,271 newtons. So we've managed to solve for tension. From here we can just do the net torque equation again, just pick a different reference point to try to figure out what F1 and F2 is, or we can use our net force equation. So we can look at net force in the X is going to be 0. So we look at our forces acting in the X, which are only 2. We have the F1 and the X component of the tension. So that means the X component of the tension and F1 have to be equal, and since we know what the tension is, we can plug that in, and we find out that F1 is 1,460 newtons. To find F2, we're going to look at the net force in the Y direction. So we know the net force in the Y direction has to equal 0. There is 4 Y component forces acting on it. There's the F2, the weight of the box, and the Y component of the tension. So we know when we add up all these forces, those 3 forces. Can I hit that one there? And then we clean it up. and we find out that the force 2 is equal to negative 1,440 newtons. Now, the reason we got a negative number isn't just because the F1 is actually acting in the negative direction. The reason we have a negative number is because we apparently didn't draw F2 correctly. If we do everything based off our diagram and we end up getting a negative value, it doesn't mean that it's pointing in the negative direction. It just means that we drew it in the opposite direction that it should be. So again, the answer is negative because F2 should be pointing in the opposite direction of our diagram. Not just because it happens to also be pointing in the negative direction. It's the opposite. So then we calculated all our three forces and we're done.